Welcome back, everybody, and I hope you've had a good break. I'm genuinely sad this is the final session of the VSSW conference. However, I'm super excited about the three thought-provoking talks we have lined up for this session, which is entitled Snow Properties and Changing Environments. To introduce the speakers in this session and to keep us on track and on topic, I'm pleased to pass you on to Bruce Jameson. Bruce, over to you.
All right. Thank you, James. Snow properties determine how and when avalanches release, as well as how avalanches flow. In the first presentation of this session, we're going to learn why the flow characteristics sometimes change from the top of a path to the bottom of the runout zone. The second presentation is a remarkable study of an avalanche with unusual characteristics in the start zone. The third presentation is about regional changes in the snow climate and how these changes can affect avalanche formation. This session is sponsored by Avalanche Canada, the home of public avalanche safety in Canada. Okay, and thanks again to Avalanche Canada. Our first speaker is Dr. Jan Thomas Fischer. He works as the head of the Division of Snow and Avalanches at the Austrian Research Center for Forests, contributing to the unanswered questions in avalanche research. Jan Thomas Fischer is also actively involved in the avalanche education programs, as well as the recently founded Austrian Association for Snow and Avalanches. Collaborating with other researchers in Austria and Switzerland, he recently tackled the question of how temperature influences snow flows, which is what he will speak about today. I'm keen to learn about why some large avalanches have a powder cloud high in the path and transition to a wet flow in the runout zone. Over to you, JT.
Thank you, Bruce. Thank you, everybody. Thanks for having me in the last session of the VSSW. Got prepared 2 years ago in Innsbruck with this hat, and I'm still liking it and still wearing it. I'm really proud to present here on flow regime transitions and the thermal equilibrium in avalanches. I really want to thank my co-workers from the University in Vienna, BOCO, which is Kilian Heil, Roland Keitner, and Ingrid Dreiweger, and my co-workers from Davos, which are Anselm Köhler and Betty Sovilla. So, what we're talking about today is a little bit of a journey on snow. Most, as Bruce already said, most of the snow is just laying around, but we actually talk about snow that flows. So snow is a material, it lies around, and we know that snow is actually pretty hot. Not only in the sense of skiing or snowboarding, but just as a material property. If you take the homologous temperature, which is the temperature of the material itself related to the melting temperature, then snow would be something like melting lava. So for example, translating minus 10 degrees Celsius, I don't know what this is exactly in Fahrenheit, but it's kind of cold, would relate to a homologous temperature of 0.96. The same temperature of lava or rock that is flowing around would be more than 1000 degrees Celsius, so pretty hot. So what we need to remember is that hot materials really like to undergo changes. Snow is really wanting to change, especially when it flows. And this we all know from avalanches. So avalanches exhibit different flow regimes. They exhibit cold powder flow regimes or warm dense flow regimes. A lot of times in the past, but still now, people talk about mixed forms of avalanches. But what we learned, or what I'm going to show you now, what we saw in a lot of studies looking with radars at avalanches, that these regimes transition from one to another. So we start as a cold powder snow avalanche, but we might end up as a warm dense flow. But this is not only the whole story. So transitions can happen partially or complete. So if you would like, you can see this video of this avalanche actually on YouTube. I posted the link here on the slide, and it should also be in the chat right now. You might not believe me, but you can watch it yourself, but this is exactly the same avalanche. So in the upper part of the track, we have a full-on powder snow avalanche, which is associated obviously to cold temperatures. And in the bottom of the part, we have a dense wet flow, which is obviously associated to warm temperatures. Everybody knows this. If we look at the radar picture of these avalanches, we can distinguish in different types of transitions. For example, a partial transition would be an avalanche that transitions from cold to warm, but not fully. This means that the run out is still dominated by the cold part of the avalanche, which is really fast. In this radar picture, bottom left, you see the blue dot, which approximately ends at a distance of 150 meters and 25 seconds. So this means we have a really fast avalanche coming down the mountain as a cold powder snow avalanche. And then way later, at approximately 250 seconds, you see that the tail of the avalanche, which is a warm dense flow, stops at approximately 600 to 700 meters distance. So this we would call a partial transition. In the top, you see the associated velocities that we recorded with Doppler radar data, and kind of give the same picture of the velocities of the avalanche. A complete transition in turn would look like this. So this is again Val de Lacion, right-hand side on the picture. You see the mast. Who's familiar with the Val de Lacion knows what this is. And on the left-hand side, you see again the radar data. Red colors are really high intensity. Yellow colors are not that much intensity. And if you look again, you see that there's a really fast flowing avalanche in the beginning, which is associated to cold flow and stops at approximately 800 meters distance, then transitions quickly into and completely into a dense flow that travels very slowly. If you look at the radar velocities in the top of the pictures, you see that this is below 5 meters per second, so it's pretty slow, but continuously keeps moving and moving for approximately almost 400 seconds, and also ends up at the bottom of the slope. So the only difference between the two avalanches that you can see from a total runout distance is not that big, but the type of deposit or the type of flow that reached the bottom is really, really different. We try to summarize this and parameterize it. So we introduced the so-called transition index. A negative transition index indicates a partial transition, so avalanches that are dominated by cold flows. A positive transition index indicates dense flows. That's why you, for example, also find the so-called Moos avalanche, the one that you can see in the YouTube video, on the top right end of the scale, which means it is very much a complete transition. We saw the deposits, really big granules, and it's a really wet flow. The interesting part at this graph that I didn't explain so far is that we plot the transition index versus the cold to warm altitude. The cold to warm altitude indicates the altitude where the snow cover, and I'm going to explain what I mean by snow cover really soon, transitions from the -1 degree, let's say, limit. So, and the snow cover here means that we did a lot of snow cover simulations of the top 50 centimeters of the snow cover. And when this transitions from -1 to warmer temperatures, we call it the cold to warm altitude. And what we see is that the flow type, or the transition index, which is connected to the dominating flow type, really correlates to this transition, really correlates to this altitude. And the question is, what is the process driving these processes here? Is it friction? Is it entrainment? It's pretty difficult to see this in the field experiments. The good thing about this index is that it might allow us in the future, for example, if we know this cold to warm altitude, to predict which flow type is going to end up at the valley bottom. And when we know which flow type is coming, we can, for example, decide which kind of mitigation measure is the correct one for this exact date and properties. The problem is the driving processes that really underlie the whole thing kind of in disguise for us. We don't know what we're dealing with. And this is why we have to perform laboratory experiments. Laboratory experiments in snow have been done for a long time, and we use very sophisticated experimental material. For example, in the 90s, already in Japan, people used tumblers, but recently again, people use tumblers again to check what kind of flow regimes exist in tumblers and how do the granules distribute and what sizes do we get. One thing that we could recently learn with Walter Steinkogler in Davos is that this -1 degree transition is really important. So above -1 degree, so everything that is between -1 and 0 is really warm, and you have a formation of a lot of granules. It's not a really strict transition. It might start a little bit earlier and go on for a little bit longer, but it really depends on this temperature. Also in these experiments, you can relate liquid water contents to the existing flow regimes and things like this. So these experiments already tell us a lot. But what did we do? We took a rotating drum, a little bit bigger tumbler that you see here in the picture, and put in 100 liters of a, let's call it a lab avalanche or a little snow flow in the lab. And this tumbler is then running at a constant speed. So you get flows of approximately 10 centimeters high. The velocity is like, I would say, running. So it's like almost 2 meters per second. And densities that you have in there are approximately around 340 kilogram per cubic meter. So what is the trick that we played? You see there's a little bar on the right-hand side in the pictures, and this is a temperature measurement. And now I'm gonna let you have a look on the experiments that Brand is gonna play for us. So now you see the camera view in the drum, and you see how we are measuring the temperature while the snow moves. And you see how slowly more and more granules form, and the flow transitions from a cold granular flow to cohesive warm flow. Also, what you see at the same time that the velocity profile is entirely changing towards a plug flow. That's not the matter for these experiments, but it's also pretty interesting. So why are these experiments interesting? If you look at the temperature measurements that we perform in this drum, we get a little bit more information than on the tumbler experiments. And the good thing is we can reproduce the results of these tumbler experiments. In the graph on the left, you see how the temperature of the snow in blue is evolving. So we start with a snow temperature of approximately -8 degrees. We have a really rapid heating in the beginning of the flow, and then at about, I don't know, 500 seconds or something, the heating rate decreases. And at about 700 to 900 seconds, we slowly pass the border of -1 degree. And you also that there's a little wiggle in the temperature measurement, which means, oh, we have granules and the temperature measurement is not that accurate anymore because there's also air between it. And finally, we get a lot of granules in our flow. We are really happy with this because this is what we expected, and we could reproduce the previous results, and this already makes you happy if you can do this in some kind of experiments. The problem that we had later on was that we did not always saw what we expected. So here again, you have a little picture of our drum, and you can do a little thought experiments, putting yourself into this drum, and you just think about that the drum moves forever and ever and ever. If the drum keeps moving forever, we would probably call it a finite steady state movement. So if something moves forever, at some point it should get hot, and at some point everything should disappear, and no, first we get granulation, but at some point everything should probably evaporate and nothing is there. The problem that appeared in our experiments is that we had a bunch of experiments where simply nothing happened. And this is what we call the no granulation dilemma, because you expect granulation, but you can't see it. And now I'm gonna invite you to look at this dilemma yourself. Brand, next video, please. This video is pretty short, but I promise you that we could play it forever and simply nothing happens. There's no granules forming, the velocity profile stays the same, density stays the same, everything stays the same, simply nothing changes. So let's have a look at the temperature evolution in these experiments. We again start at about probably -8 degrees Celsius. We have a rapid heating, and then suddenly the heating decreases and we go into a thermal equilibrium state, which means the temperature is not changing anymore at about -4 to -3 degrees. So it's kind of obvious that we also don't get granulation, because this is what we expect at -1 degrees. And then we start asking ourselves how this can be. And looking at the ambient temperature, which would mean air temperature in this case, we see that this was at -5 degrees for this experiment. So what actually happens is, after rapid heating, at some point the snow has the same temperature as the air, and the heating that the air also had on the snow before switches into cooling and balances all the frictional heating, and we reach an equilibrium state. Now we are the ISSW, and the formulas are appreciated by everybody, but this slide we have to look at, because the interesting part about this slide is that at the top you see the formulation of the temperature evolution, and at the bottom you see 3 equations and only 2 processes that are described by these equations, and this is all you need to describe the entire process mathematically. So the temperature evolution depends on the starting temperature, on the equilibrium temperature, and on the time where the 2 temperatures, the ambient and the snow temperature, coincide. We plug in dissipative heating. Dissipative heating means we have movement, so we have dissipation, so we have warming, and the ambient exchange of energy, which means heating or cooling from the air. And putting these processes together, and this is all the math we need for the whole model, we already can derive the full model. The very interesting part, and this is shown in orange, is that there's only very few free parameters in this. So we can measure everything that is written in blue, and we can measure everything that is written in orange. And this could not have been done like this before, because we can actually measure shear stresses and the heat transfer coefficient of snow, and the shear stress is something that is very much related to friction. So we can also deduce some kind of friction process that is behind the whole thing. Which is a very nice side effect of the model. And the other nice side effect of the model is that it actually works. So if you look at this, there's blue measured temperature, and the purple one is the air temperature, and the black line is the model temperature, and we put one on the other and it fits really well. This is what we want to see. The problem is, and that is shown on the bottom or listed at the bottom, we only have very few of these experiments because they were kind of accidents, but still good enough to derive a new model. If we look at all these experiments at the same time, this you usually do in a normalized way, non-dimensional. So here you see plotted the non-dimensional temperature versus the non-dimensional time. You see that all these experiments are pretty well overlapping the prediction. Colorful dots are our measurements, black line is our model, and all of this is pretty much on the same line. Why am I showing you this plot? Because the question is this relevant? Yeah, and you see that, for example, if you look down there and you have a bit of an idea how big stresses are in the snowpack, for example, for stability or something, you see that the stress is measured here, and these experiments are pretty low. But if you scale this up with the flow heights and the velocities of real avalanches, and you look at the times that we measure, we actually end up with scales where this thermal equilibrium can happen below a minute. So during the flow of an avalanche, this effect could really have an effect on a flowing avalanche in the field as well. In summary, we saw that we have flow regime transitions in the field which exist. We are able to describe them, we are able to relate them to some kind of properties of the snowpack, but it's really difficult to find out what is driving them. Maybe friction, maybe entrainment, we don't really know. In the lab experiments, it's a little bit easier because we can switch off a lot of side effects that we cannot control in the field. We're able to reproduce earlier results that really confirm this -1 degree limit, which is really important if you want to make snowballs to throw them at your friends. And but the most important thing is that we discover a new effect, which is this thermal equilibrium in flowing snow, which is pretty interesting. The other thing that this might go into in the future is to put these small models in big models for modeling avalanches, so we can predict with like what are the circumstances for having certain flow regimes, what ends up at the bottom. The question that Bruce asked in the beginning, is it going to be a powder snow avalanche that hits me at the bottom, or is it gonna, can I still run because it's actually just a wet flow and I have a lot of time? So the mobility and type of avalanche that ends up in the runout zone is pretty much where this could go in the future. And then I say thank you to you all, and thank you for SSW.
Okay, thanks very much, JT. That was great. That's some good solid science and a wonderful explanation of it. We're now ready to start the discussion. You can click on the hands up icon, and if you prefer, you can also type into the chat box, and we have Olivia and Nicole standing by to read your questions if you do prefer the chat box. So, Brent, do we have any hands up?
We currently have no questions from the floor, Bruce.
Okay. So maybe while we're just waiting for a few people to stick their hands up or to type into the chat box, JT, how do you think we're going to change that in the avalanche dynamic models? What are they going to look like in the future to incorporate this temperature-based flow transition?
Okay, so I mean, there's people that have been like Perry and our French colleagues and Cesar in Switzerland also. A lot of people have been working on the influence of temperature on avalanches and try to model wet snow avalanches. Mostly the problem is that the picture that we have of snow somehow ends up to be a snow picture. Yeah, we only think about one material. And this is for avalanches the same, especially in modeling, because we usually consider them as shallow flows that move as a continuous medium. But what we forget that it is a mixture of air and snow, and they flow in air. So we usually really consider what is at the bottom. Is there more snow that we can take in or something like this? But what we barely consider, there's really few models, but they are computationally really expensive, that actually consider to take in air. These are usually powder snow avalanche models, but for the normal models, we don't take into account the interaction with the air.
Yep.
And
okay,
this,
great.
especially for wet snow avalanches, could be interesting.
Okay, great, thanks. Brent, do we have any live questions from the hands up?
We still have no questions from the floor, Bruce.
Oh,
looks like we have one out of the chat box, though.
How about Olivia, Nicole? Do we have any from the chat box?
Yeah, you bet. We have a couple questions. The first one is coming from Nathan, and Nathan asks, were you able to model flow based on particle speed and density morphology from an initial to mid and deposit?
In these experiments, I'm not 100%, I get Nathan completely, but so what we also did in these experiments is trying to look at the density evolution while we have granulation, but the problems that arise, so the drum has a lot of more sensors. We measure flow depth, we measure forces, but everything gets really confusing as soon as you have a transition, as something changes. The beauty of these experiments is that you have a steady state. And when you have a steady state, then you can really average and measure things nicely. And once you have granulation, you can estimate densities, but you usually get bulk densities of the whole flow, which are not really representative for a single granule. So this is, the data exists, but it's really difficult to interpret it.
Yeah. Okay, thanks, JT. We got, hopefully we have more questions, and we got 90% of your answer. You were a little bit broken up there because of the technology, but Olivia, do we have more questions from chat box?
Yeah, we got a couple of questions rolling in here. This one is from Clancy. How much do you think the confinement of the flow affects transition? A tumbler is confined like a narrow, well-defined avalanche path. What about situations where the flow can spread out?
I would probably say that for the effect that we are looking at, which is the interaction with air, that probably more confined flows are less influenced by it. And this is probably also why powder snow avalanches really like to be associated to flat terrain or open terrain, because they can spread wherever they want. And maybe this is just an assumption, or just pops up in my mind right now. Maybe they can breathe a lot of cold air, which makes them survive even longer, because with more cold air, they can compensate for the frictional heating. It's not fair to extrapolate the results of lab experiments that far, but maybe this could be an answer to the question.
Okay, and Brent has thanks very much, JT. And Brent has a hands up question for us.
Hi, we have a hands up from Rupert Wedgwood on the floor. Go ahead, Rupert. Hello, Rupert. Looks like you're unmuted, but we cannot hear you. Give you one more second there, Rupert. All right. Looks like we're going to move on to the next person there, Rupert. The next person in line, I believe, was Nathan Neisel. Go ahead, Nathan. Hi, Nathan. It looks like your mic is very muffled. We don't hear much other than some squeaking there.
Or later on in the afternoon. Is that okay?
There we go, Nathan.
It's really busy right now. Okay, it's gotta go.
Nathan.
Hey guys, sorry. Just wondering what modeling software you guys were using, or if you had also used sort of a historical avalanche sort of threshold data to compare actual versus reality.
Okay, so I think now you're rather referring to the transitional avalanches, because for the good thing about these tumbler or this drum experiments is that we don't need any software. This is like hands-on mathematics and one formula. And in the transition, for the transitional avalanches, the software that we need is Snowpack and Alpine 3D to estimate this cold to warm altitudes. So
okay.
There's a lot of snow cover modeling involved to get this altitude. And then there's also another study, which was also done by Anselm Köhler, where they compare the outcomes of the radar measurements to open source software. But this is shallow water modeling like RAMS or SAMOS or anything like this for avalanche modeling. But this was not included in this study. In this study, it's only pretty much Snowpack and Alpine 3D.
Thanks for your answer. We're looking into the modeling side. So very fascinating stuff.
Okay, thanks very much, JT. We're going to cut off the questions, and perhaps there'll be more that will trickle in the chat box that JT can check. But excellent presentation, and thanks for the insightful answers.